And hello, viewers of mine. So we are continuing on from our first video on the big five acceleration equations. We had kind of talked about this at the end of the first video, but I want to make sure this is very clear. So I'm just kind of recapping for the second video because the first video's learning target, and it's so important that we have these learning targets. That learning target was I can choose the appropriate big five equation to use based on information given in a word problem. So let's say you're given whatever information. You have your list of variables. You have oops, go back, silly. You have an initial velocity, final velocity, acceleration, and you're asked for displacement. Well, you could go through and try to choose an equation that has initial velocity and final velocity and acceleration and displacement. But that's going to be very time consuming. So if you look at these equations, as I said before, there are a total of 5 equations and there are 5 total unknowns. And that is not a coincidence. This is why I set it up this way. Each equation only has 5 variables. Okay, so that means, or excuse me, each equation only has 4 variables. There are 5 of these equations. That means there's 1 variable missing from each equation. And that is exactly how you're going to choose which equation to use. As in, if I'm given the initial, final, acceleration, and displacement, and I don't care about the time, in other words, I'm not given the time, nor am I asked for time, then I'm going to choose the equation that doesn't care about time. So here's my list again of the equations. And I say, hey, which of these equations does not deal with time? Well, there's time right there. Time is in that one. I would use the 4th equation. The VF squared is equal to VI squared plus 2AD. Okay? What if I were given a different list? So initial velocity, final velocity, acceleration, displacement, time. So I'm given initial velocity, I think I'll skip final this time. I'm given acceleration and displacement, and now I'm looking for time. But I'm neither given final velocity nor asked for final velocity. So which equation does not care about final velocity? Well, that would be this 3rd equation here, the 1/2 AT squared equation. Okay, so that is the equation I would use. Good stuff, good stuff. Now, let's pretend that was question part A. And then in part B, it says, well, now go ahead and solve for the previously unknown variable. So in that case, that would be the final velocity. So now we want the final velocity. Well, let's see. I still have the initial velocity. I still have the acceleration. I still have the displacement. And technically, I just solved for the time. So you say, so which equation should I use? Can I use any of them? Well, any of them that has final velocity in it? Yeah, sure, I guess so. But you know what? I did just solve for the time. What if I made a mistake? I can use these other 3 much more confidently than I can use the time. So I'm going to say, let's ignore the time. Let's pretend we don't have that in case we did make a mistake. So which one doesn't care about time? Ah, the VF squared equation. Lovely, lovely, lovely. Okay, so to solve for the final velocity, I would use the 4th equation. When I was solving for the time, I would have used the one that didn't care about the final velocity. That was the 1/2 AT squared. Okay, good stuff. Physics. Now, here's our next learning target. This is for problem solving techniques. I can set up and solve a problem in a clear and thorough manner, showing all the physics steps. Indeed. So, what are all the physics steps? Reading the problem thoroughly. You say, well, duh, of course I'm going to do that. You'd be surprised. Read it several times if necessary, but definitely read it thoroughly, because sometimes it's super obvious. They say like, hey, the velocity is this and the acceleration is this. A lot of times it's kind of hidden in there. Okay, sketch a picture and draw a velocity time graph. It doesn't need to be any type of beautiful picture. If I'm saying, oh, a car is driving down the street, okay, fine. Here is a terrible picture of a car, but you get the idea. And we're driving along here, and the initial velocity and the final velocity over some type of displacement, and I've got an acceleration. Okay? That's what you can draw. You don't need to say, oh, well, I don't like that car. I'm going to draw like this type of car. This is my favorite type of car. It's got a bumper sticker. No, who cares? You can draw a box and label it car for all I care. But you do need to label the physics. So you got to have the units, or excuse me, the variables in there: initial velocity, the final velocity, the acceleration, the displacement. That's going to be very, very important as we move through. And also draw a velocity time graph. And you don't need to show any of the scaling on here. You just say, hey, this is velocity, this is time, and this is what the car is doing. Boom. This is telling me that we started at some positive velocity and we're increasing speed. Boom. Nice. Okay. Let's see. We got our sketch, and then we got to list out our knowns and our unknowns. Okay, so similar to what we had just talked about on the previous slide. Remember, there are a total of 5 variables, 3 of which you'll be given, 1 you'll be asked for, and 1 you won't really care about. Next, think about what you're trying to solve. This is another one of those duh. And I'm going to say, yeah, early on it's going to be pretty easy and straightforward, but then as time passes, we'll get to more and more challenging problems, and you'll be like, what? Or sometimes you're given information that you won't necessarily need or won't necessarily use the way you might think you would. So it's important that you're really thinking about it. Then select an equation, solve for the variable. Okay, notice I didn't say plug in anything yet. Write out the equation in the original form, in letter form, and then I want you to rearrange the equation in letter form. Okay, the reason I'm having you do that is because you're less likely to make mistakes when you're moving letters around instead of numbers around. It's easy to flip numbers, less easy to flip letters. Okay, and I want you to see patterns. After a while, you'll see, oh, solving this problem, this is the same as that problem I just solved like a few problems back. This is the same thing, no problem at all. Okay, you rearrange the equation, and then you substitute in the values, and that includes with the units, and calculate. Then you say, okay, I'm all done, right? Well, one more step. You check by estimation, units, and reasonability. If you end up with units, you're trying to get acceleration, and you end up with like meters squared per second, well, that is not the correct unit for acceleration. So you know you did something wrong. Having the correct units doesn't guarantee you're correct, but it's at least a good sign. Checking by estimation means you're doing some rounding. Maybe you can do these calculations kind of in your head and say, okay, I'm pretty close. Maybe the answer is 50 and you got 20. Well, that's not that far off. You said, what are you talking about? 50 and 20 are not the same thing. Okay, if you got 50 and the correct answer is 5 million, that is far off. But if you got 50 and the correct answer is 20 or 80, that's not that far off, relatively speaking. Okay, and then reasonability. Does it make sense? Does it make sense for the final velocity of your car to be greater than the speed of light? I will tell you now, no. No, it does not. That would be bad. Okay, now there are a lot of things you may not know about just yet, but for example, most cars won't be going anywhere close to that. Or for that matter, anywhere above the equivalent of 100 miles an hour. So if you got a vehicle going like more than 50 meters per second, probably not. I mean, we'll see. Maybe airplanes, certainly. Okay, let's see. Let's go ahead and do an example problem. So we got to read the problem first, of course, read it very carefully, and then we got to sketch things out and so on. So a baseball pitcher throws a fastball at 44 meters per second. Assuming the ball's displacement from behind his back to all the way forward is going to be 3.5 meters per second. What is the ball's average acceleration? Okay, so we went ahead and we read it, and now we should start drawing stuff out. So let me get a lovely sheet of paper up here. Okay, so I have this set up here as kind of a sketch pad here. So I have a baseball pitcher, and the baseball pitcher is throwing, right? So I'm going to draw, let's see, in red apparently, or black, the baseball pitcher. And here is the baseball pitcher with the rather large, long arm. This is where the ball starts off, and this right here, so I will label this as the initial velocity. And then slinging over here, this is going to be the final velocity. This whole dealie right here is going to be the displacement, and the ball is going to be accelerating forward like that. So in other words, the ball is speeding up. That's what this picture is showing us. Now, you say like, oh, well, no, I want my pitcher to have this uniform and this. No, no, no. We're just showing the physics involved. In fact, if you just want to say, hey, here's the ball, somehow the color just changed to red. Here's the ball, and here's my initial velocity, and here's my final velocity, and got my displacement. In other words, it's a D. In other words, if you're just going to totally bypass the person, that's fine. Okay? The important part is that we're showing these variables so we can say, hey, this is what's going on. Right now, it looks pretty basic. Why are we bothering with this? Well, right now, it's moving in one direction. That's pretty easy. It'll get harder. Okay? So now let's go ahead and list out the variables. So we've got initial velocity, final velocity, acceleration, displacement, and time. Okay, and what do we have? We have, let's see, we've got 44 meters per second. I'm not sure if that's initial or final velocity. I'll have to get back to that. Moves forward 3.5 meters. That sounds like a displacement to me, 3.5 meters. We're looking for the acceleration, so that's my question mark. Okay, and then, oh, shoot. I don't know which velocity it is. It says baseball pitcher throws a fastball at 44 meters per second. So seems to me that the pitcher is trying to get it to get up to 44 meters per second. So that would be the final velocity, right? Okay. Guess we didn't have the initial velocity after all. Oh no. What? We only have two variables, and this is our unknown. This is what we're looking for. Fair, you swore. You promised me. You told us that we would always have three givens, and we'd be looking for one unknown, and that we wouldn't care about the fifth one, right? This is an example of when we have to think about what we're trying to solve, look at what we're given, think, right? In other words, it's not given as a number. We do have to interpret. The baseball pitcher throws the ball. Initially, in other words, right back here, the ball isn't moving. So that's going to be 0 meters per second. Okay, so a lot of this is interpretation. Okay, that means I don't really care about the time. Okay, and I can finish drawing out my sketch. That means I can, let's see, draw a velocity time graph here. Velocity time graph, and label that my initial velocity was 0. My final velocity is some positive number. I mean, it's 44, but I don't really care. And so that means my acceleration is going to be nice and positive. Good. Okay. So I've got my list, and I already drew out my graph and my pitcher, right? Or would that be my pitcher? Right. Okay. Next step is to choose my equation. So let's change colors here, so it's a little bit easier to follow everything. Orange, lovely. I don't need you. So, which equation does not care about time? Okay, that would be the VF squared equation. We mentioned that several times already. Times already. Oh no. Just stick to the physics fair. VF squared equals VI squared plus 2AD. And for those folks that use, instead of D for displacement, use delta X as displacement, fine, whatever, it's not a big deal. Okay, let's see. And then you need to rearrange, you need to solve for the acceleration. I don't want you plugging in any values yet, with the exception of if anything is equal to 0, because that'll just make it a lot easier. And looky, initial velocity is 0. So this part will go away. Vf squared is equal to 2ad. Lovely. And I'm trying to solve for the acceleration. So divide through by twice d. And I get acceleration is equal to Vf squared divided by 2d. Now, since I've rearranged everything, I can go ahead and plug in pink. Stop that. And that's going to be, let's see, V final was 44 meters per second. So that whole thing is squared, divided by twice 3.5 meters. Okay? You tap that into your calculator, that's going to be that's 1936 meters squared over seconds squared over 7 meters. Notice I am keeping the units with me, and the meters there, or the square cancels out with the meters there. So that's going to be acceleration is equal to 276.57 meters per second squared. That's way too many sig figs. Let's just round it and say 280 meters per second squared. You say, congratulations, all done, right? No, you still need to check. So let's change the colors again. Actually, let's skip red and go to indigo. All right, so we actually already checked the units. The meters per second squared, that's a good sign. Let's go ahead and check through estimation. So in other words, round things off and say, is it approximately that? So instead of saying 44 squared, because I don't know what that is off the top of my head, I mean, I could use my calculator, but I could say 40 squared, and then divided by 2 times 3.5. Well, I can actually calculate that in my head, but I'm not going to divide by 7. That's just kind of a weird number. Okay, maybe I could divide by 5. I mean, that's pretty close. It's not that far off. So 400 squared is going to be 1600. Okay, divided by 5, that is 320. Is that the same thing as 280? No, but that's super duper close. Okay, you said, well, fair, instead of dividing by 5, I chose to divide by 8 because, you know, it was supposed to be 7, and 8 is even closer, so mine is even better. Okay, fine. 1600 divided by 8. Okay, 16 divided by 8 is 2, so that's going to be 200. Okay. Is that the same thing as 280? No. But is it super close? Yeah, relatively speaking. Yeah. So that means checking by units and estimation both work out. Checking for reasonability. Is it reasonable to have an acceleration of 280 meters per second squared? Well, that's a tough one because we don't know much about it just yet. We don't know enough values to say, is that reasonable or not? But we can say the acceleration has to be pretty darn huge. We're going from 0 meters per second to 44 meters per second. Remember, that's about 100 miles an hour in a very, very short time. So that acceleration is going to be really, really large. Okay? Is it going to be 280? I don't know. It's going to be more than 5 or 10. Okay? So it's not unreasonable. Is it reasonable? We'll see with other ones as we continue through. Okay? All right, so, I wasn't clicking. So I got the baseball pitcher. There's my list. As we said, final velocity rearranged, plugging and chugging. We get that, 280 meters per second squared. We checked our answer with units and reasonability, and then through estimation, we got approximately the same value. In fact, you might even call it a ballpark figure. Oh my! You see, ballpark. It's a joke. You see, a ballpark would be an estimation ballpark figure, but it's a baseball pitcher, so this is in a in a, in a ballpark, so it's okay, fine. All right, let's continue on. Okay, and yeah. By the way, this method of showing all of our work here is super duper important because if you make a mistake somewhere, and if you're not showing your work or it's not an easy thing to follow, then physics teachers, we want to be able to give you partial credit. But if we can't follow along with your logic, we're not giving you anything. Okay, so that's why we have the pictures and stuff like that. This is also referred to as pies sometime. You might say like, pie. Okay, well, what I mean by pies, that's an acronym. So pies, that stands for picture, and then information, and then equation, and then solving or solution. You can say it that way too. Okay, so pies, Pies, that's the idea behind it. Okay, so if you want to call information, list, it's the same idea. Okay, all right, let's get the next problem on here. Car acceleration. Okay, so we have a car with a velocity of 2 meters per second at at t is equal to 0 seconds, accelerates at a rate of positive 4 meters per second squared for 2.5 seconds. What is its velocity at time is equal to 2.5 seconds? Okay, so we've read it. Let's go ahead and draw this out. Doesn't have to be anything beautiful. Here's my car. Remember, you can draw a box and label it car. Doesn't really matter that much. But the important part that does matter is the physics involved. So you got to show the variables. And let's see. This is my initial velocity here, my final velocity over here. It does show a positive acceleration, so I'm going to be speeding up, okay, over some type of displacement. Yeah. Okay, remember, I don't actually need or even want the numbers to go in there. Why not? Because I'm going to be seeing it's the same basic idea of what we just solved for with the baseball, right? It's the same picture. Okay? Huh, that's kind of cool. All right, let's go ahead and see how similar the next part is. Is the list going to be the same too? Well, I mean, it's the same variables. Are they going to be the same values? No, of course not. Let's go ahead and solve for that, or fill this in. Let's see, it says if a car has a velocity of 2 meters per second at 0 seconds, well, 0 seconds implies starting time. So that's going to be my initial velocity, 2.0 meters per second. And let's see, accelerates at 4. Okay, so that was very kind of it to say the actual the acceleration is this. Lovely. Okay, and we're saying what is the velocity? So that's my question mark at 2.5 seconds. Lovely. Sounds to me like I don't care about displacement. So you think, what equation will I use? Well, while you're thinking of that, I'm going to be drawing in the velocity time graph. Remember, it doesn't need to be any type of numbers in here. We're just getting the basic feel. Okay. There. See, very, very similar to the one before. The only difference, folks, is that the one before started at 0, and this one started at some positive value. But the slopes, I mean, I'm not actually showing numbers, so all I can say is this about the slope is positive and constant, right? Yes, yes, good. Okay, let's see. Okay, so let's go ahead and do the equation, the one we don't care about, displacement. So that's going to be VF is equal to VI plus AT. Lovely. Hey, look at that. It's already rearranged. Man, physics is so delicious. Okay, so let's see. The initial velocity is going to be 2.0 meters, emphasize that point, per second. The plus acceleration is going to be positive 4.0 meters per second squared. And then the time is going to be 2.5 seconds. Okay, gee whiz, do I even need a calculator on this? It's going to be 2.0 meters per second plus, let's see, 4 times 2.5. Hopefully we can figure that out in our heads. That's going to be 10. And then meters per second squared times seconds, it's going to be meters per second. So look at that, the final velocity. I didn't even need a calculator. Boom, that's going to be 12 meters per second, right? Right. Am I done? No, of course you're not done. You got to check your work. Okay, no, it's what the cool kids are doing after all. So the units did work themselves out. Final velocities units should be meters per second. Let's go ahead and do an estimation. Final velocity is, and this is my estimation, say 2 plus 4 times, I don't know, like I could do that in my head. I'm going to say 4 times 3. Okay, sure, yeah, 4 times 3 is 12 plus 2. So V final is approximately 14 meters per second. And yeah, that's practically the same as 12 meters per second. For an estimation purpose, this is good stuff. In other words, can you do it in your head, and is it approximately the same? And is it reasonable? Is it reasonable for the car to be going at 14 or 12, this is the correct answer after all, 12 meters per second? Yeah, that's a very reasonable speed. That's like 25 miles an hour or something like that. That's not a problem at all, okay? Speeding up for a few seconds, yeah, you can get up to 25 pretty reasonably, okay? Good stuff, nice. So that was it for this problem. Now, I will ask you, what would happen if part B of this problem, which there isn't a part B, but let's pretend there's a part B. If part B says, okay, now go ahead and solve for displacement. How far did you go during that time? Well, we still have 2.0 meters per second, and we still have positive 4.0 meters per second squared, and we still have 2.5 seconds. Okay, now I'm looking for displacement, and hey, don't forget about the 12 meters per second though, right? Sure. Okay, but I'm not absolutely sure about that. I'm pretty sure, I'm very confident actually, but what if I made a mistake? So I'm going to say, no, do not use the 12 meters per second. Don't use the final velocity. So what equation would we use if we don't care about the final velocity? That would be d is equal to VIT plus 1/2 AT squared. And then you would go ahead and plug in and solve. Oh, look, it's already rearranged for us. You'd plug in, boom, boom, boom. Okay? Of course it's okay. It's physics, which is delicious.